problems. I thought I did a really good job. And then I went to watch it later and there was no sound. My microphone was dead. Oh, my pen is gone. All right, so first thing to do is sketch that function. If you haven't already tried, please do so. Let's see, x equals y squared, square root of 15 from y equals 0 to y equals 1. So let's see, if y equals 0, x equals 0, so I have a point here. And if y equals 1, x is the square root of 15. Square root of 15 is pretty close to 4, right, for x. Because the square root of 16 is 4. So there's y equals 1. So let's see, a solid lies between planes perpendicular to the y-axis at y equals 0 and y equals 1. The cross sections perpendicular to the y-axis, all right, are circular discs with diameters running from the y-axis to the parabola. So this parabola is sideways parabola, right? And so it's going to go something like that there. And we're concerned about y equals 0, which is the x-axis, and y equals 1, right there. Y-axis, x-axis, and let's see, the diameter of any circle is going to be perpendicular to the y-axis, starting at the y-axis and running up to the edge of this parabola. So if I pick some random y value like right there, then that distance right there is one of my diameters of the circles. Diameter. All right, making progress there. That's an arrow, by the way. So there's circles popping out of the plane perpendicular here. Can I draw that? Oh my gosh. Well, the biggest diameter is up here, right? From there to there. And the smallest diameter, well, that's just a single point at the bottom. So if I draw this sticking out of the plane, like tilting the plane a little bit, there'll be a big circular top. That's that distance at the top there. And did anybody know what the diameter of that top circle is going to be? Square root of 15, yeah. So that's this value right there, just before 4. So at the top, we have a diameter of the square root of 15. And then straight down from that, there's a point. And this is 1 unit high, right? That way. And then it slopes over to that edge over there. So think about a cone, right? So what we have is a funky looking cone with one straight edge. And so it's circular, coming around like that. Okay, so that's what this object looks like. So now we need to figure out what the volume is. And so in general, when we're working with cross sections, we're going to integrate through some distance whatever the cross-sectional area is. Okay, so what does that look like for us here? Well, each of these lines is a diameter of a circle, so our cross sections are circular. The diameter of one of these cross sections, d, is equal to the distance from the y-axis over to that point over there. Now that's a horizontal distance, right? So what variable expresses horizontal distances? X. So it's going to be x equals stuff. So some function of x. And we are told x is equal to that right there. So if we're starting at x equals 0 and going up to that number, then that means that expression right there are our cross-sectional distances. So that would be the square root of 15 times y squared. Now, I need to turn that diameter into an area. How do we turn diameters into areas? Okay, what's the area of a circle? Pi r squared. How do we turn a diameter into an area? Sorry, into a radius. Divide by 2, right? 2 radii? Okay. So if that's the diameter, then the radius has to be equal to square root of 15 y squared over 2. And the area would be pi r squared for any one of those circles. So new page, a cross-sectional area here is going to be pi times our radius, square root of 15 times y squared over 2 squared. And we need to integrate that as y goes from 0 to 1. So cleaning that up, our volume should be the integral as y goes from 0 to 1. And we're going to have some constants there, right? We're going to have square root of 15 squared. We got our pi. We got a 2 squared, which is 4. And now we have a y to the 4th power. So that should be the integral that's going to give me my volume. All right, so pulling out the constant pi 15 over 4, and antiderivative for y to the 4th. Y to the 5th over 5, integrating from y goes from 0 to 1. Isn't too bad. That's going to be 1/5 minus 0. So then I get pi times 15 over 4 times 1/5. That didn't come out right. And that cleans up just a little bit since 5 goes into 15 3 times. So it looks like our answer is a volume of 3 pi over 4. So in any of these problems, whether it's cross sections, whether it's disk, or we're going to move on to shells shortly, the hardest part is setting it up. Once we get the integrand, it's not too bad. Key here is I was working with cross sections, so somehow I had to take this 2-dimensional picture. Did I really need the version of the 3D picture? Sometimes it's nice to have, but I definitely have to figure out what is the cross-sectional area. And so I have to play around to find a formula. And everyone's going to be a little bit different. And these are harder to check because we don't have programs that are easy to work with to kind of generate these volumes at the moment. Yeah, I haven't had time to play with GeoGebra yet. I'm hoping to find some time to play soon. All right, let's try another one. In GeoGebra? Oh, I can just plug it in right here. All right, sure. What did we say it was? 3 pi over 4? 3 pi over 4. Nice work. All right, let's try another one. Darren thought 15 was interesting. And let's back this off a touch. Okay. Oh, good. I wanted to do one of these today. Find the volume of the solid generated by revolving the region bounded by the parabola and the line y equals 1 about the following lines. Okay, so I'm not going to do all 3 parts, but I'm going to do one of them for sure. So what do we have? We have the region bounded by y equals x squared over 4 and y equals 1. All right, so sketching that region in the plane is part 1. So let's see, y equals 1. So let's put 1 right there. And then x squared over 4. So if x is 1, y is 1/4. We have 0. So let's see, if x is 2, 2 squared is 4, then I get y is 1. All right, and then similar on this side with -1 and -2. I get points over here and over there. So we can view this as either a vertical compression or a horizontal stretch of the standard parabola. So we have that region right there, and we want to revolve it around, where'd you go? Y equals 1, x, y equals 2, y equals -1. All right. So we'll do the first two. So here is the line y equals 1. We already have that drawn in the picture. And I mentioned when you do these, always draw the axis of rotation with a little arrow around it just to remind yourself what you're doing. We're using what's called the shell or the disk method, which means we have a little area that's perpendicular to the axis of rotation that we're going to move around. In this case, since my axis is horizontal, my disks are going to be vertical, and the little dx is that width of the disk there once I rotate it there. So we're going to generate disks that look like that with a thickness of dx. And so we need to come up with an equation for the radius of the disk. Well, the radius of the disk, if this is the axis of revolution, is just this distance right there, right? Okay, so let's see, how do we generate that distance right there? Well, it's a y, so my radius is going to be y. And I start up at the top at y equals 1, and it drops down to y equals x squared over 4. So any radius should be 1 minus x squared over 4 are the radii here. Because I need to find what is the distance from here to there. And whenever we find distance, we take the larger number minus the smaller number. Since y is going in that direction, 1 is the larger number, and the function value is the smaller number, right? So it's got to be 1 minus the function value. Okay, so we got that, and then what do we do with it? Well, once I have the radius, to get a disk or a little thin cylinder like that, it's just pi times the radius squared times the thickness of the cylinder, dx. So for our integration here, we're going to spin it, and then we need to consider x is going from -2 to 2. And we get pi times parentheses. My radius is 1 minus x squared over 4 squared dx. So now we need to come up with an antiderivative for that. Thoughts? Yeah, expanding, it's our only choice here. If we tried to do a u substitution, the main candidate for u would be the inside of the parentheses. And so just to check on that, if we let u equal 1 minus x squared over 4, then du would be what? Negative 2x over 4, which should be what, negative x over 2 dx. Do we have an x hanging outside of that parentheses? No, which means this substitution doesn't do us any good. Yeah, so our only choice is to square that out. All right, new page. So let's see, do I got that right? Yeah. So we've got the integral as x goes from negative 2 to 2. Pi can come out, and then we're going to square the 1 minus x squared over 4. So to be safe, you probably want to write it out as 1 minus x squared over 4 times 1 minus x squared over 4, so you don't make any mistakes. So what are we going to get when we're going to do that? We're going to get a 1, and then we're going to get minus 2 of those x squared over 4s, and then we're going to get negative times a negative is a positive x to the 4th over 16. And pi is still hanging out front. X is still going from negative 2 to 2. And the only thing I can really clean up there is the 2 over 4. Could be written as 1/2. And I guess I don't need that 1, do I? Okay, so now we're at a point where we can find an antiderivative. And I could clean up the boundaries a little bit if I know about symmetry. So just double check. Do we have any symmetry we could use here? Yeah, the left half and the right half are equal, because if we replace x with a negative x, we get the same function back, right? So it is definitely even symmetric. So we could just double the integral from 0 to 2. And plugging in 0 is usually a pleasure in problems like this. So let's do that. So I'm going to put a 2 out front there, and I'm going to cross that 2 out and put a 0 there. So then when we evaluate this guy, what do we get? 2 pi square brackets. Antiderivative 1 is x minus, let's see, x squared is x cubed over 3. So that'll be an x cubed over 6. And then plus x to the 4th becomes an x to the 5th over 5. 5 times 16, 80. And we get to evaluate that from 0 to 2. Does plugging in 0 make everything completely disappear from the minus part? Answer is yes. You should always really think about that just to make sure. Don't take it for granted. And then we just have to plug in our 2. So we've got 2 pi times 2 minus 2 cubed is 8/6 plus 2 to the 5th, 2, 4, 8, 16, 32. 32 over 80. And whipping out a calculator, we're going to get some repeated decimal there. We're probably going to want an exact answer here, so we better do some arithmetic. What does it say, exact answer? Yep, using pi, so we got to do a little arithmetic on that sucker. It's always nice to have a calculator that does fractions at this point. So let's see, what do we got? This is really 4/3. And let's see, 80 was 5 times 16, right? And 32 is 2 times 16. So this is what, 2/5? Did I do that right? 16 goes in the top and bottom. So my common denominator is 15ths. My tools are gone. Shit, I didn't want to do that. So was that a 5 down there? Okay. So with a denominator of 15, let's see, 2 would be 30/15ths. And let's see, the 3 needs a 5. 5 times 4 is, so I'll have a minus 20 there. And then 2 needs a 3. 3 times 2 is 6. So it looks like I'm getting 16/15ths out of that. Does that look right? Okay. And 16 times 2, it looks like it is 32 pi over 15. Let when we clean it up. We got some head nods there. Okay. And again, were this a test, I'd be much more careful with my arithmetic. Now, if my antiderivative is correct, GeoGebra can whip that out. Okay, so the hard part was setting that up. So we could always plug this into GeoGebra and get an approximation and see if it matches that, provided we set everything up right. So let's check that and then try the next part. So what do they say? 32 pi over 15. All right. All right, we get an excellent. Okay, here comes the fun part. Y equals 2. So we need to redraw this picture because we're going to have a new axis of rotation and we totally messed that one up. So new page. So our function is still y equals x squared over 4, bounded at the top by y equals 1. There we go. So top boundary, and oh, did I just? Yeah, that's right. I have right there, and then this is a nice parabola. Oh wait, that's wrong. I'm thinking of the problem before this one. Let's see, 1, 2, 1, 1/4, and then other side, 1, 2. So here's our parabola, and we're taking that area, and this time we're going to spin it about the line y equals 2. And again, this line right here is y equals 1. And that guy right there is x squared over 4. So when we spin this one, we're going to end up with a hollow center, right? Can everyone picture that? So I'm going to have a hollow center, and then it's going to have a curved outside, kind of barrel shaped like that, and it's going to be flat when I look through it. Okay, so this is going to make this funky kind of barrel with this curved outside. Kind of looks, yeah, kind of looks like an olive. Oh my gosh, cool. We're making a mathematical olive. Nice, with the pit taken out. So in order to figure out this one here, we need to identify a couple of things. Let's go to red for a second. At any point in here, if I slice through this thing, I'm going to end up with a washer type shape. And for a washer, you need to identify what is the big outer radius, capital R, and then what is the inner radius that gets removed. Because to take a washer kind of shape, you're going to have pi big R squared minus pi little r squared times the thickness of it, h. Okay, so what is our big R? What is furthest away from the axis of rotation? X squared over 4 is what's furthest away. So big R here is equal to 2 minus x squared over 4. Right? I need to get from here to there. And whenever we find a distance, it's always the bigger number minus the smaller number. And would you guys agree 2 is above this function at that point? Yeah. Now, that's kind of irrelevant because we're squaring that number anyway, so if we get the subtraction backwards here, it's no big deal. But there are times in these calculations where if you screw up the order of subtraction, you get a negative answer in the end. But because of the square of the radius, it's not going to be a big deal. What's little r going to be then? Is going to be 1? Yeah, so little r is the distance from the axis of rotation to the closest thing that's getting revolved, which is y equals 1. So it's going to be 2 minus 1, which is 1. That one's always the same. Sometimes they both vary. Sometimes they both will have variables in it. It just kind of depends. So when we do that, we're going to take these little thin rectangles of area and we're going to revolve them, which is going to generate these washers here. They're micro thin, right? And then we just add them all up, and that's what the integral does. So we have to turn this right here into our integral. What's the thickness of my washer H in this case? That's dx, yeah. So just that lets me know I'm integrating with respect to x. Okay. All right, let's throw that into an integral. So I'm gonna see if I can squeeze it into the bottom here. So I think for my volume, I want the integral as x goes from, I'm gonna go with the original boundaries from -2 to 2 for now. That's a negative. And this is kind of complicated, so I'm gonna put in outer parentheses. Let's use a different color for now. Okay, so I have pi times my big radius squared, so pi times 2 minus x squared over 4 squared. And then I'm going to have minus pi times my little radius, which is 1 squared. And then I close off that and multiply by the thickness of each washer, which we're calling that dx here. So that is my integrand to get this volume. What's that? Oh yeah, we can certainly pull out the pi. And then we can also say, hey, we've got symmetry here, so we could double this and go from 0 to 2. So let's try to rewrite it, cleaned up a little bit. So new page, what color do I have? Blue, let's go to black. So we're gonna do 2 for the symmetry, we're gonna pull out the pi. That means we're going with x from 0 to 2. And then, what do we have here? Okay. 2 minus x squared over 4 squared minus 1 dx. And like last time, a u substitution is not going to help here because I don't have a du to go with it. So we're going to have to multiply this sucker out and then clean it up algebraically. So let's do that. So what are we going to get? 2 squared is 4 minus 2 times that is what? Negative x squared over 4, and we'll get 2 of those. Better write that down. So there's going to be 2 of 2 times the x squareds over 4. And then we're going to have a plus x squared over 4 squared, which is x to the 4th over 16. And don't forget, we still have a minus 1 chilling out over there. And this is where I might, want to, on a side piece of paper, like I'm kind of pulling this out, if that part seems confusing, actually write out 2 minus x squared over 4 times 2 minus x squared over 4, and then carefully distribute just to make sure. Okay, so I kind of thought that in my head and wrote down that blue stuff above. So I'm going to pull this out for now. Okay, how does that clean up? 4 minus 1 is 3. So back to my integral, 2 pi integral as x goes from 0 to 2 of 3 minus x squared plus x to the 4th over 16 dx. You guys on the same page? Okay, pretty sure I didn't mess up any algebra or arithmetic there. And now antiderivative, 2 pi square bracket 3x minus x cubed over 3 plus x to the 5th over 80 from 0 to 2. And the 0 zeroes out, so all I have to do is worry about the upper boundary. So 2 pi times 3 times 2 is 6. And let's see, that's going to be 8 over 3. And then 32 over 80. Doing all right there? Reduce and find a common denominator. 8/3 does not reduce, but 32 over 80 is what, 2/5? Common denominator is 15. What's 6 times 15? 90. So we're going to have 90 fifteenths. And then 5 times 8 is what, 40 minus 40 fifteenths plus 6 fifteenths. 90 minus 40 is 56 fifteenths times 2 pi. 56 times 2 is 112. So I think, if I didn't screw up my arithmetic, I have 112 pi over 15. And again, something I might do at this point to double check that. How many people have a GeoGebra or a TI at hand? Something similar. So if we set up our integral correctly, we could just ask the TI or GeoGebra to give us a numerical approximation on that and hope it matches that. Now that checks to see if we got the right definite integral, provided we set the integral up in the first place, right? And that's the complicated part. And I can't do it without drawing lots of pictures, reminding myself which R's I'm playing with, thinking about the radii and what the washer looks like. Okay, so if you think you can do these without drawing all of this stuff, I think you should draw all that stuff. I don't know how you could do it without it. All right, so what's that? You draw a lot of pictures, and that's one thing in that quiz for chapter 6 I put up there, quiz 1. I want to see pictures drawn. I want to see work, just to make sure everything's right and people are writing stuff down in a way I think will make you good calculus problem solvers. What's that? Yeah, so if I'm not going to do that one, but I'll sketch it. So with that one right there, we've got our parabola chunk here, right? And that's y equals 1 up there. Y equals -1 is down here. And that's going to be our axis of revolution that way. So then looking at that picture, I need to identify from my axis of revolution what is big R and then what is little r. So just getting it partially set up, it looks like big R. What's furthest away from the axis? 1, right? Y equals 1. To get to the axis, I take the bigger number minus the smaller number. So big R should be 1 minus -1, which is a distance of 2. Does that seem reasonable? Okay. Little r, on the other hand, considering that function is what, y equals x squared over 4, should be the distance from that function to y equals -1. So here y equals, the function is on top, so it looks like little r is x squared over 4 minus -1, right? Which I could say is x squared over 4 plus 1. And then I plug those into my integral, which is, you could pull the pi out if you want, big R squared minus little r squared. In this case, it's going to be a dx again, when we draw those little rectangles, because if I'm doing disk, the rectangle is perpendicular to the axis, so dx. So pretty similar to the last two. Find the radius and then start working it out. All right. So let's plug that number in just for fun. What do we get? 112 pi divided by 15. Woohoo, good job. We should have got a fantastic on that one. That was tough. Okay, so there was another problem here I wanted to do, and I didn't write down the number. Did I even assign it? I think I did. It should be near the end, maybe 17. I'm not done. Yes, I want to leave. Oh, that's a cool one. Should we calculate the volume of a donut? Okay, that's a cool one. Yeah, so, huh? 3? Okay, the donut, that's a cool one. And then this one is cool. Did you guys do related rates last term where one thing changes, look at another thing change? This one's kind of cool. I think I'll save this one for tomorrow. Give it a shot. If you get stuck, we can do it tomorrow. You gave up on that one? Okay, so what? All right, so what would you rather do, the related rates or the donut? Donut? Okay, we'll do the related. Try the related rates. If you get stuck, you can do it, finish it tomorrow. So let's do the donut. Okay, so, and they're giving us a hint here. This is, and we'll see it when I draw the pictures. This is the integral for the area of a semicircle. Semicircle would be the area of a circle divided by 2. That's going to pop up when we solve this problem. So what we're going to do is we're going to take the disk, x squared plus y squared is less than or equal to a squared. So here they're differentiating between a disk and a circle. A circle is the edge, a disk is the inside. Okay. So let's draw that. This one's fun. And so we are going to take a look at the graph of x squared plus y squared equals a squared. So if I say this is a up here, then a is about here on the x-axis. That's the y-axis. Negative a would be about here, and a is about there. So draw your best circle radius a. And let's go with blue. So here is mine in 4 pieces. That's not bad. All right. And then it says pick a value b that's bigger than a. Okay. So if that's a, I'm going to put b out here, and then I want to consider the line x equals b, and that's going to be our axis of rotation here. X equals b. Now, since I'm revolving around the a vertical line, then that means I have these horizontal things that I'm going to revolve. And so I'm going to end up with these giant washers like that. And so I need to figure out what is my big R and what is my little r here. Am I working with dx's or dy's on this? dy, right? Because that's this little piece right there. Yeah. So it's dy. Okay, so that's going to be a dy. And I think that my big R is going to be that distance right there. Okay. And so this is some x value right there. And so the distance from here to here is going to be b minus whatever that x value is. This right here tells me how to calculate those x values. So if I solve that for x, I'm going to get x equals plus or minus the square root of a squared minus y squared. So this side over here is the positive square root, and this side over here is the negative square root. Okay, all right, x is positive on this side, x is negative on that side. So this blue side, is that the positive or the negative side of the root? The negative side. Okay, so that means over here, I'm going to have b minus the negative root. And according to up there, that root is a squared minus y squared. That's big R. which cleans up to be b plus the square root of a squared minus y squared. Little r. Let's see, little r would be this edge right here over to the axis of rotation. Okay. B is bigger because it's further to the right there. So little r is going to be b minus this x value right there. How do we calculate that x value? The positive square root this time. Yeah, so it's going to be b minus the positive square root of a squared minus y squared. Okay, so big R is b plus the square root, little r is b minus the square root. Okay. And we're going to be integrating, that's a negative a down there, with respect to y as we go from negative a up to a. And we're going to be collecting a whole bunch of these thin little washers. And when we stack all those washers up on top of each other, we've just made a giant donut. Okay. All right, so now we get to build the integral. So the integral for something like this, y equals negative a to a. We can pull the pi out, and then I have my big R squared. Big R is b plus the square root of a squared minus y squared. So I have to square big R. And then minus little r, which is b minus the square root. Oof, how are we doing on time? Oh man, we're not going to finish this one. Bummer. Squared. And then all of that with respect to y. And before we can find an antiderivative, guess what we're going to have to do? We're going to have to square out each piece. Yeah. No, it's not. Let me just show you what this one's going to look like, and then we're out of time, so we're going to have to stop. If you multiply that by itself, you're going to get a b squared plus 2 of the product of those guys. So that's 2b square root of a squared minus y squared. And then you're going to get plus the square of the square root, which is going to be what? A squared minus y squared. And then I'm going to have to square that one out and then change all of the signs after. Right? So I might as well just write that down. I'll just take a sec. So if I square the other one out, I'm going to get a b squared. I'm going to get, and I'm ignoring that minus for now. I'll put that one in a minute. I'm going to get a minus 2b square root of a squared minus y squared. And then negative times a negative here is a positive. So then I'm going to get plus a squared minus y squared. What do I do with all of that next? I subtract it, right? So if we subtract, that means this becomes negative, that becomes positive, this becomes negative, that comes positive, and some wonderful stuff happens here. A whole bunch of stuff vanishes. The only thing that's left is going to be 2 of those guys right there. So we went this far, what the heck, let's go one more minute. So now it looks like we have pi as y goes from, oh, do we have any symmetry here? Yeah, we do have some symmetry. We could just do the top half of this donut. Bottom half is going to be identical. So we could double the integral from 0 to a. And we have 2 of these guys. So that means I have a 4b square root of a squared minus y squared dy. Let's see, the 4b pops out, right? What does this equation right there represent? A semicircle, yeah. So what we're going to get is, in the end, we're going to get 2 pi times 4b, oops, whoa, times the area of a semicircle. What's the area of a semicircle of radius a? Pi a squared over 2. So we're almost done. Let's see, cleaning that up. This 2 divides that 2. Pi times pi, that's wild. The donut has a pi squared in it. Huh, interesting. All right, we'll double check this formula tomorrow with a slightly different method. But it looks like the volume of a donut is 4 pi squared a squared b, if there's no errors in this algebra. Oh, I'm off by a factor of 2 somewhere. Interesting. Okay, so there's a slight error in the algebra. We'll find that error tomorrow, or if you're bored tonight. Keep working on the 6-1 homework. We didn't start 6-2 yet, so we're officially a day behind. That's okay. I'll adjust dates if next necessary. Hit that Ask Your Instructor button if the tutorials online don't help. Yeah.